Welcome to Semantic Web Technologies. This is Lecture 4, Knowledge Representations, Part 2, Ontologies in Computer Science. In the last part, we have investigated the concept of ontology in philosophy. But for us as computer scientists, of course, we have also to take into account what ontology means in our subject, in our domain of reference. So, what is an ontology in computer science? There, I can give you a rather brief and concise definition by Tom Gruber, who has been specified this definition already 20 years ago. So this is only one definition amongst many other definitions, but it's concise and it captures almost the most important things about ontologies. And the nice thing is it's only, or the important part is only one sentence, and this is the first sentence of the definition here. So he says an ontology is nothing else but an explicit, formal specification of a shared conceptualization. And he says the term ontology is borrowed from philosophy, where we know that an ontology is a systematic account of existence. For artificial intelligence systems, this existence part means what exists is that what can be represented. So this is the interesting thing for us. So the most important thing or part of this definition is the first sentence. An ontology is an explicit formal specification of a shared conceptualization. But what does that mean? We have to define each single word. What does it mean exactly? So what is a conceptualization, first of all? A conceptualization is nothing else but a model. So what we try to do is we try to form a model about a domain we are talking about. And inside that domain, we try to identify the relevant concepts and how these concepts are related with each other. So this is a conceptualization, a model. This model has to be explicit. It means all meanings that are defined, the meaning of all concepts must be defined. Nothing has to be left out. So everything must be defined you are talking about. Then this definition, of course, must be formal. Formal means it must be understood by the machine. It must be machine understandable. Not only machine readable, but it must be interpreted correctly. Only to read it and to interpret it correctly means that you understand it. So, machine understandable. And one of the most important things is, of course, the things you are talking about must be shared among communication partners. So this model, this conceptualization, must be a shared conceptualization, a common conceptualization. There must be consensus about the ontology. Why? Just simple, otherwise you can't communicate. So for communication, we know this semiotic triangle. We have already seen that. So you know in language, you have a symbol, for example here, jaguar, which means a word in a language. This stands for a certain object. But language is ambiguous, so there can be several meanings. Jaguar can stand for the cat, for the car, or for the operating system. And you only can talk or communicate with each other if both of the two communication partners or more communication partners apply a shared concept. If they share the same concept, then communication is possible, then understanding is possible. This is the only way. So, these are the basics. The next question is, how can we represent ontologies, or how should we represent ontologies in computer science? So, take into account we have to form a model, and several components of this model we have already named. So, components and models of an ontology. First thing of all, you have to identify classes. Classes are sets of things. They represent concepts. They can either be concrete objects of the real world, specific objects of the real world, or they can be abstract concepts. And you can describe classes via their attributes. It means the individuals populating these classes, they share certain attributes. So they have something in common, therefore they form a class. For example, the class of all students, the class of all professors, or the class of all peoples, even more general. So, the attributes describe the class, and attributes itself can be given by name-value pairs, for example. And then you can describe these classes in a more informal or in a formal way. For us, of course, it's important to make a formal definition. We have heard that in defining what an ontology is, you need a formal specification. So informal means it's only given in natural language. So the problem is natural language cannot necessarily be understood correctly by a machine. So you have to give a formal representation. More formally here, for example, you have a semi-informal description of what an address means. But in the end, you have to give a formal specification. It means you have to go back to logic. And how to do that, we will come back to that later. The classes itself, I have told you that, are related to other classes. So classes are related to other classes. Pretty simple. Let's take the simple example. We have already defined the class of professors and the class of students. And all these two classes, of course, are subclasses of the class person. It means that a professor, of course, is a person. And a student is also a person. On the other hand, each person has one or more addresses. So the class person is related to the class of all addresses by a relation that is called has an address in that case. On the other hand, a professor gives a lecture and a student visits a lecture. So that's pretty simple. So these both classes are connected to the same class lecture, but via different relations. And the lecture, of course, is a subclass of all the courses that are available at a university. To give a more formal definition of what a relation is, you should have seen this already in set theory. So when here the classes are represented here as sets M sub 1 to M sub n, then a relation R is defined as a subset of the Cartesian product of all these sets. So pretty simple. And in the end, also these relations can be specified as class attributes, only that then the attribute values are other classes. So it should be pretty simple, and you will see this in the exercises. Okay, but we can represent more knowledge. Up to now, we only have classes and relation among these classes. You can put further knowledge to these relations. For example, to relations and attributes, you can constrain them. You can determine which values are allowed and which values are not allowed. What makes sense, what doesn't make sense. For example, here, you have again the class person, and you have the two subclasses. You have women and you have men. And both, of course, are subclasses of person. But on the other hand, one individual that is really a component of this class man cannot be at the same time also part or an entity of the other class, of women. So these two classes are disjoint. So it means if you make an intersection between women and men, then there should be the result, the empty set. And this is a constraint that we can put among two classes. So these two classes have a relation, and the relation says that no individual of one of them can be at the same time in both of these classes. So it's pretty simple. On the other hand, you can also put number restrictions on these relations. For example, you can say there is a one-to-one relation between a student and a person. So a student can never be two persons. So that makes no sense. On the other hand, you can say a person can have more than one address. So this is pretty simple. You have there a 1 to n relation. So these are constraints. So more knowledge, more semantic that can be put on relations or on specific attributes. Then, with classes, relations, and constraints, you put them together, you can form statements and assertions. So you can make a logical statement. And a special case of these statements are so-called axioms. An axiom is knowledge that can't be expressed simply with the help of other existing components. So you need this axiom to make sense. And this is not part of the formal definition of the basic set of constructs, of classes and of relations, but it's something as a rule. For example, you say it is not possible to lecture two courses at the same time, because then you must be two persons. So this is not possible. Okay, the last thing that is missing in our model are the individuals. It means we had classes, which are sets of individuals, and now we need individuals that can be member of a class. So individuals or instances are the basic components of an ontology. So individuals may include concrete objects, for example, peoples, animals, tables, automobiles, or anything else, as well as abstract objects like numbers or words, or even abstract concepts like love or revenge. So here, for example, you have a class, seminar, and you have a specific instance of that class, which is a seminar called Linked Data Application Engineering. And also you have given specific attributes or relations to attributes. It means it takes place at a specific time and it is located in a specific room. So this is an instance, and instances or individuals, they populate the classes and they populate the ontology. Okay, but this is only the basics and the conceptual model. What we want to do next is we want to take a look at ontology types, ontology examples, and in the end we want to see, to know how to represent knowledge with the help of logic. And this is very important. You need this formal model and you need this logic to make calculations, to be able to make, in an automatic way, inductions or deductions. It means that you are able to draw conclusions and that you can make implicit knowledge that is given somewhere inside a knowledge base explicit, and you can deduce new knowledge. So we will see that in the next parts of this lecture.